So it seems that we've arrived at the last day of the second week of OPLSS. You know, I'm sure that all of you are ready for 2 more weeks of more fire hose. Yeah. So good morning, everybody. Okay. So you're all bright and shiny-eyed because you've been crying, because your brain hurts. But we're going to do one more gradual typing session, and then I'll pass the mic off. So what I wanted to do today is kind of go through 3 things. Like last time when I left off, I'd kind of just gotten to like a touch of the idea of gradual typing as it has appeared in the research literature. I've mostly been telling you the story about combining languages that statically checked or statically enforced type disciplines and dynamically enforced type disciplines, and giving you some of that context. And then I've walked you through these languages. So we started with a few, and then I'll write down some details here. But I wanted to say what I'm going to do today is I'm going to talk to you a little bit about the broader context of gradual typing. I might make this, I'm going to make this a lowercase g for reasons that I'll explain. And then I'm going to give a shout out, and then I'm going to do a magic trick. I'm going to pull a rabbit out of a hat. So what I want to do first is kind of give you the story of like how to think about a lot of the literature on work in what's kind of broadly called gradual typing. The reason I say broadly called gradual typing is a lot of the stuff that I am going to talk about today and that I write about is but one piece of this effort to try and combine static and dynamic checking of programs, possibly using types. And it's a broad history. There's a deep history, and there's also a broad horizon. So we're kind of looking at the frontiers, and I want to just kind of say, like, given all the things that you've seen so far, how can I kind of translate what people are up to into the terms that you can understand based on what I've said? So we started with our tale of 2 languages. We had BA, and then we had TBA. And then I built this together. We kind of just took the 2 of them, mashed them together, and that gave us MBA. And then I kind of started squishing further down, and this was what gave us this sort of minimalist language that I called MMBA. And then at that point, it was kind of like mostly static with just a little bit of dynamicity in it. But you could basically understand both of these languages and this one in terms of this language, which kind of boils things down. And then the last kind of step on yesterday was to kind of talk about the idea that we can think of what was going on here, which looked like a programming language construct, as something at the type level. And that's where I would call it like gradual BA. Now we'll use a big G for this one. GBA, but I didn't actually fill out the language. But that's what we're going to do today. So from here, what I wanted to talk about was like a few ideas related to what happens in the world of gradual typing. So you've kind of seen the sort of big picture that I'm talking about in our issues. And first, I wanted to point out a couple conversations that we've had along the way. And I also wanted to relate back to what Sam does a bit. So the trick I'm going to play today is I'm going to pull this rabbit out of this hat, which is to say, imagine that the BA language never existed. Like you lived in a world where everything was calm and static types roamed the prairies, and then suddenly somebody decided, like, maybe I do want a program where the 2 branches of my conditional don't produce the same kind of value. You're like, like scandal, So, but you have revolutionaries who figure out like how to think about this language and be able to use it to kind of invent this language. Now, it's not particularly, it seems sort of not as interesting in a certain sense because this one already exists, but there's something really beautiful about the idea that it's the type structure of this language that makes this one come into being, that I'm thinking at the type level. Like down here, I gave you this little hint that like, oh, I move everything into the types, and you're like, oh, this could be just kind of a bait and switch thing. And it's like, yeah, there's casts underneath them. And my point is like, that's not really the point. The point is that thinking about the type structure can help you induce a totally dynamic language or even one of these in-between languages. Now, what's the kind of payoff for that in general is, suppose what you want to do is, let's imagine that you like dynamic languages and you want to figure out, how do I write a monitoring system for a property that I'm interested in? Some random property. And like usually you're like, oh, I'm going to add contracts to my language or something like that. Well, or what you're thinking in terms of, I want to add a dynamic feature to my language that allows me to check some property. Now, remember, properties are kind of metalinguistic, right? It's like a property of my language or a property of my program. And that's exactly what types are, right? Types are neither static nor dynamic. They are metalinguistic, and you can enforce them statically or dynamically. So if you can use types to describe the property that you care about, wouldn't it be cool if that kind of structure could build you an assert system so that when you write an assert in your language, you're really writing like a static type you're writing a type, I shouldn't say a static type, you're writing a type claim, a metalinguistic claim about a property of a part of your program that ends up happening to get enforced dynamically. It's kind of like, oh, like contracts are the new types, or types are the new contracts. Beautiful marriage. So this is a really neat idea if you can understand your property using this sort of type level discipline. And that's really like nice for even a dynamic language writer who's like, yeah, they don't know that we're using types for our asserts. Isn't that sweet? Like, you know, right? So as opposed to just random checks. So it's like you have a reason to know why it works. And some kinds of checks that you want to do in a program are hard to come up with. It's hard to think about, how do I enforce it? So it's nice if the discipline that you often think of statically will help you do the dynamic. However, there is something funny about this approach, and this is kind of how I always think about gradual typing, is I take a language and I kind of pull it all the way back here, and then I have this sphere. But the first day, there's a thing that seems a little bit funky about this, because we're sort of like, our tendency is to think, you know, in the beginning there was BA, and BA was precious and we loved it. And then people started writing big BA programs and they started breaking, and so we added types so that we could keep people from killing one another across the cubicle farm. So often we start with a language over here, you know, already. So we could say, oh, we have BA, and then later on, after we've written a bunch of programs, we think about, oh, people are writing programs and programs are lighting on fire. Please stop. And so we try to say, like, how are we going to reel this in, right? And it's like, oh, I know, we'll use types. We'll add a type system to it. And this is a hard research problem. I would sort of claim that I've managed to avoid this altogether. Sam, who is a far braver or maybe younger, more energetic, and not strategically inclined person, has decided to take this on like full steam. And what kind of issues does this raise? A lot. And this is what comes into this sort of extrinsic viewpoint on types, where you say, I have a language, it already exists, I can add a type checker to it and reason about it, or add a type checker to parts of it and reason about it. The hard part is this. People are already programming in this language. If any of you have been programming for long enough, you've seen what happens when, you know, Perl 5 tries to become Perl 6, when Python 2 tries to become Python 3. Like, people get angry when you pull their language out from under them. It's like, you know, you've broken my toys. Like, you once again updated the interface to Facebook, and now I can't find my friends. So there's this thing that if you create another language going this way, which in the case that the specific case I'm talking about is going from the idea of there being a language called Racket, which already existed, to typed Racket, which is sort of the reverse of what I did over here. That's because I'm a theorist, I get to do this. It's like, yes, of course there was a typed language first, because I can invent what I want as long as set theory says it's okay. But, you know, the pragmatics of this field are that many people are trying to fight this problem of there existed Racket, there existed Smalltalk, there existed JavaScript, and I need to somehow tame it. And one of the challenges is the way I describe it as conveyed to me from on high by Matthias Verleisen is that programmers program different programmers program with different informal type systems in their head, by which he means informal reasoning properties. And setting aside the fact that they may not be sound, they may not have like proven a theorem about them, they can have fundamental differences in style and understanding and reasoning power and sort of taste. And this can even boil down to a single person may program with multiple type systems in their head, with different styles, with different tastes, with different motivations. So how do you manage to design a language that has a type system on it that's going to satisfy a broad base of users that already exist? I think the secret to that is create a cult, tell people that you're right, and then smash them. But it's not that simple. It's actually, you're very constrained in this world, and this is a really hard problem, and people have been working at it in different contexts. Like Jeff Foster, who's a researcher at University of Maryland, has been trying to do this with Ruby for a really long time. How do we do like typing for Ruby? And the challenge is like, which Ruby programs do you allow to fall on the floor? Which ones are you going to say like, it's okay if this is not going to, if our fully static system is not going to accept it? And that's a hard problem in general. And in a sense, this I was thinking about this yesterday, and it goes back to our conversation where I rudely said you were totally wrong about something. But the wrongness was it was a purely technical point. So if I can recap, can you remind me your name? I'm sorry. Scott. So the technical point that was being made was that the worry was that by going to this language here, which smashed out all the statics, I was somehow sacrificing the dynamic language. And the sense in which I said, no, that's not the case, is that I'm just going to say, like, I can always have this, and I can always make every one of these work in here, and I never have to see this. It's an intermediate language. So that was the sort of small technical point. But there is a major conceptual point that is really worth thinking about, especially in this context. Because I just said that you have to decide which programs you're going to like statically remove. And in a sense, the way I did this language here, every feature of the language had statics to it, right? There was a static if, there was a static pred, there was a static bool. Everything could be precisely typed. But in this world, you may have to make sacrifices. You may have some features of your language that are just plain red. And I think that was really the concern that was being expressed here. Like, what if there's something that I don't know how to bluify or sorry? Any question? Oh, laughter. Oh, okay, good. We like laughter. I was like, no, they're all gonna laugh at me. Yeah. So that you may end up with a language that can't type everything, where you try to type as much as you can, and then you accept that some parts of your language are going to be blue. And an example of that in the context of this project is how the object system in Typed Racket works. It has a really sophisticated class system. Classes are not types. Classes are first-class objects. And there's been a line of PhDs done over here on first, how do I dynamically enforce properties, and then how could I possibly type this thing? And then sacrifices have to be made, things have to be left imprecisely typed, but you can at least get some traction. So I'm kind of describing a research program we'll call the forward version of what I'm doing, which is saying, assuming that this existed already, how do I tame it? And in that world, you don't have the ideal that you can push precision all the way down to everything. You have to make some sacrifices. And for many different languages that are out there in the field, that's a problem. You know, that's a hard thing to do. Yeah?
Just a general question, but in the program that you're describing, is the type checking all assumed, is the goal to make it all static, or is it like a mixture of static and dynamic type checking? And by dynamic, I mean just in terms of contract or something like that, right?
Great question. So the question is, in this program that I'm talking about here, is it all static, or is it a mix of static and dynamic enforcement? The answer is the latter. It's a mix of static and dynamic enforcement, partly because this system has this feel to it. In many ways, the world of Racket was the inspiration for MBA, and that's only part of the reason, because you do have these typed modules and you have these untyped modules. The other thing is, some of these things are going to be imprecisely typed because I started over here and I don't know how to type them yet. And so those end up having to have dynamic enforcement if you use those features. You may end up using only features that can be precisely typed, but you have the ability to use features that we don't have the power to statically enforce. So this is where having a goon squad of wicked Northeasterners and like the people all over the world like hacking on your runtime system and building this crazy macro system that you can write language after language after language on top of comes in handy, because you need to actually instrument your programs. So this is also an intrinsic program, but it's left to right is how I would describe it. This is where the way I think of sound gradual typing is like you're doing intrinsic stuff. You are changing the semantics of your runtime to enforce properties. So then so this question's a great setup for me, because then it's like, well, what about the fully static one? So that could be, an example of that is, the various projects for trying to write a static type checker for, say, JavaScript, where you check programs, or you check parts of programs, and then you spit out JavaScript, or what you'd call erasure semantics. People will say you type check and then you just erase, and you use a runtime that existed from back in the day when there only existed something like this. I'll use this as my titles, I guess. Your static world, your dynamic world. So then this is the sort of intrinsic style. And then there's extrinsic, which is in many ways, I would describe it as focusing on the static type discipline as a static analysis of your program, and having to deal with the fact that it's really hard to analyze these programs, and you may not even be able to guarantee that if your program passes a type checker, that it will satisfy a certain it's not necessarily sound with respect to the semantic type system that you had in mind. There's a classic example of this that I might be able to it's worth pointing out specifically. That's why I'm doing this. Okay, and full screen, and let me pop this up for a second. So this is going to be in the context of TypeScript, a statically typed version of JavaScript. So this is from a paper that was, oh, I should put the screen down. It's from a paper that was written about TypeScript, basically. And so when I think unsound reasoning in the context of a type system on top of a dynamic language, I mean examples like this. So you have a program called it takes a string, and what's the next thing you do? Is it a string? So think about your sort of semantic typing judgment, where you have a gamma on the right with some things about your arguments, and then the thing on the left which says properties. The body of this, in my mind, should be C string in the environment, which tells me this module is expecting to be linked with a module that passes you a string. Nonetheless, in order to program in JavaScript in a way that's defensive, you still have to check and make sure that that's a string, because it might not be. That's what people mean when they say that JavaScript is unsound. And what I've been trying to tell you today is, when we say unsound, it's sort of like, oh, I know unsound when I see it. It's not that somebody had specifically written down a formal model of JavaScript and proved a theorem, but kind of given the tools that you've seen this week, you could in principle do it. You could take that intuition that something funky is going on here and turn it into a formal statement. And that's a separate thing from making a value judgment. Okay, I think it's worth having a concrete example in mind. Because the point I want to make is, the theory, there's sort of the nice thing about research is many people have many different opinions, and progress happens despite the researchers. So That's not my original idea. That comes from a philosopher named Thomas Kuhn, who wrote a book called The Structure of Scientific Revolutions, the first half of which is really amazing. It really gets you thinking like, oh, science is sociology. It's not the way that it's taught. That's not the way we're taught about science in science classes, but it's really a social thing. And having that in mind is really, and knowing about that and being aware that that's a fact, makes you feel better when your papers get rejected for really stupid reasons. I found this really helpful for my mindset, and I read it late in graduate school. So the point I wanted to make was like, you know, the theorist in me says like, yeah, like intrinsic typing, this is great. And then the empiricist will say, is sound gradual typing dead? That's a paper title, by the way, because it's too slow, right? Like, right? So that there's a worry there. The theorist in me will be like, oh, this is totally unsound. I don't have reasoning principles. The pragmatist or empiricist in me will say, yeah, but you know, for some reason we put this out in the field, and when people use it, their programs seem to crash less, and they seem to show a sign of like happiness in the world. Like there's like a plausible, testable empirical statement that could go there with, you know, graphs and charts and statistics. So you can think of this as like the deductive world, where you're sort of trying to deduce truths by working from theory. And this is the inductive world, not in the sense of induction, but in the sense of empirical science, where you're putting something out there and seeing what happens in the world because humans are disgusting, strange people that you can't understand. But you can make progress in both of these fronts. So in a way, I'm kind of talking about three separate programs that are out there in the world. And like pluggable types and all kinds of fits in here, a lot of work on type-based static analyses, which I just call extrinsic type systems. And then this is sort of intrinsic and enforcement. Yeah?
In both cases, you start with a language without type system, and then you put a type system on top of that.
In both of these, that's been what's happening. This is what I call, I guess, the forward direction, whereas what I've been talking about, what I talk about is the backward direction.
So intrinsic and extrinsic are both forward directions?
Oh, no, so it's double axes, shall we say. Like this is intrinsic forward, this is extrinsic forward. This is intrinsic backwards. In a sense, extrinsic backwards is trying to write a static type system proving safety for a language, which someone could do. They could say, oh, look, I can now prove that I can leave out all of the states. So it's almost like proving the soundness of optimizing my runtime system, saying like, I left a bunch of stuff out of my runtime system, and I can because the static analysis worked. So you can think of the possibility of extrinsic running backwards and intrinsic running backwards, and intrinsic running forwards and extrinsic running forwards. They're independent. And all of them, I imagine, have interesting questions and things that could bear fruit. Any other questions? Okay, so I just wanted to say that there's this landscape out there, and most cases when you look at a paper that doesn't necessarily talk about gradual typing per se, and the reason I wrote it lowercase g is because in many ways I use I keep the capital G for this one because this is what appeared in the original work that was done on gradual typing, the papers by Jeremy Seek early on. Now, it's worth noting that to some extent, he's doing both of these at the same time simultaneously, as well as doing that one. So he's like a triple threat, because all of these things can bear fruit, depending on what your goals are: theory, practice, immediate impact in the world, or long-term design of prettier languages, or thinking beyond this idea of dynamic languages versus static languages, instead of to maybe static languages to staticer languages, which I might talk about a bit later. Yeah?
Does the list family have some advantages in terms of typing with traditional languages? The fact that they have the same structure relative to something like JavaScript or Ruby, where you have to kind of tack it on the side.
The question was, does the Lisp family have advantages because data and code look the same? At a tooling level, maybe. Because in a certain sense, under the hood, technically, racket code is not the same thing as S expressions for various reasons that especially to do with tracking binding structure and things like that. But it has a really nice API that makes it look exactly like that's the case. So yeah, there's things about tooling that would definitely, like, what's one of the beautiful things about Lisp family languages and why it's been so good to write macros in them for a long time. And some of those things have been ported over to non-parenthesized languages like Rust and JavaScript by people who are really strong with macros. It's in the same way that like tooling for Java is way better than tooling for C++ because it's impossible to write a C++ parser. There is a company called Edison Design Group. It's like 4 people, and they make their money on writing C++ parsers, and they're really good at it. It's like, yeah, you can just write a parser for your whole life and like feed your family. That's kind of cool. So that's kind of the big picture story I wanted you to take away and know that this fits in it. Artem.
Isn't this an intrinsic versus extrinsic approach, not directly to the sound and non-sound?
Oh, so the question was, does the intrinsic and extrinsic approach map directly to the sound and non-sound? I would say yes. The way I'm phrasing it here is I'm trying to bring out technical facets of it. But I would say that's exactly right. And the reason the soundness comes in is if you were only doing fully static, wholly checked modules, it works. But it is sound. That's why type systems work when they're done on dynamic runtimes. But the moment you start linking imprecisely typed and precisely typed things, that's where soundness can go out the window because you don't have true enforcement. What you have is an interesting parser. Or linter is what I might say. But I like linter. I hope some people will view the term linter in like positively. Some people will view the term linter negatively. So maybe that's the right word to use. But I'll stick with extrinsic, intrinsic. I'll keep it technical. Linter might sound a little too heuristic and unprincipled. That's the worry that I have with that term. Yeah? Oh, the definition of sound. So remember when I talked about semantic type soundness, where I said you have a single turnstile, and then you define a double turnstile, and then you prove that if the single turnstile holds, then the double turnstile holds? That's the definition of soundness. So really, the informal thing is, does having syntactically typed my program using some sort of computational analysis actually tell me properties about my execution that's either true or kind of an over-approximation of what it might be? So it's the same issue the same issue arises in program logics like axiomatic semantics and in static analysis. To me, that's soundness. It's the same thing everywhere. The thing that's specific to types is the formal type systems, which are modular and syntax directed. So they allow you to talk about individual pieces of code and learn something by composing 2 pieces that you know something about.
Right. So when, if I remember your definition, is when a key runs through a net or whatever.
Yeah. Or so there's the semantic judgment, which is what do my types mean? I have a language, which means a syntax, and then what's the semantics of that? I have a syntax for types, which is a syntax for properties. And then the question is, what's the semantics of those properties? What does writing that down mean to me about the world, about my language? And I write it down in terms of the meaning of my programs. So that's why I say like nat means it runs to number or underflows. Good. These are great questions. We're kind of like bringing everything together. Any other questions before I move on? Okay. So a quick shout out, and this is to me non-technical but important. So I'm going to show you a magic trick. And the magic trick is the kind of the result of a long journey I've been on for a number of years. And the shout out is to a fellow who I consider my partner in crime. Isn't he adorable? Totally adorable. You're like, who the hell is that? Like, who is this kid? Okay, so I just love that picture, but really, he doesn't look like that anymore. And he's not Olivier Dumvie. So this is Eric Cantor. He's a researcher at the University of Chile. And he's still kind of cute. But really, the point I want to make is, like, I totally randomly met Eric. I was a postdoc at Carnegie Mellon. He was on sabbatical at Carnegie Mellon because he was going to go somewhere else, and it didn't work out. And he's like, okay, like at the last minute, he ended up there. And then he ended up sitting in on the class that I was co-teaching. And then he'd read a paper that I wrote randomly because I was helping my buddy Jeremy out. And then he's like, hey, are you still into this thing called gradual typing? I'm like, sure. And so that began this kind of, I think of us like, the two old guys in the Muppets, like, who are up in the bench, like, nah, 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 nah. That's kind of how, when I think of Eric and I think of that. And the thing I wanted to get across is the extent to which I don't feel like I would be standing here today if it wasn't for this person. So I wanted to give him a shout out and say, like, the thing I really like about this community is that you get to work with some really amazing people who are really interesting and excitable, and maybe decided that since being a jazz clarinetist wasn't going to work out, they would go and be a computer scientist, like Eric. And that community ends up being, really a great place to be. And so the reason I wanted to mention that is because, a lot of people I know I met at OPLSS or at other events, and I think that's a really important part of what makes this community a great place to be. So keep that in mind, because in many ways it's one of the most important parts of this, aside from the knowledge and the curiosity and the excitement. And so I just wanted to kind of emphasize, like, Bob's excitement in his going away note to everybody, where he said, he just is so excited about this stuff and wants to tell other people and talk to people. And it's great to be in a place where there's a lot of people like that. Okay, and so with that, I'm going to switch over to the magic trick. So the point is, basically, given TBA, how do we magically bring into being BA? Which is basically saying, how do we use the idea of types and type structure to induce a dynamic checking discipline? So here's where I tie back into last time. Okay, so last time I started talking about this idea of gradual types, right? Where you have the unknown type, and then you have bool and nat. And they sort of live in different worlds because of this precision relation. And precision is sort of how much information content do my types have. And the thing that's kind of cool is it turns out that if you take that view to an existing static type system, you can kind of start to get to something that gives you dynamic checking, kind of almost magically. So the question is, how does that work? So I started kind of giving you this idea last time by talking about the typing rule for if, right? So the typing rule for if was if T1 has type T1, T2 has type T2, T3 has type T3, and T1 equals bool, T2 equals bool. Oh no, T2 doesn't have to equal bool. And oh, right, okay, let me write out this part now. So this is the first side condition. I'm saying T1 has to be bool, and then I'm going to say that the result of this is a function of some of these types up here, and I'm saying if T1, then T2, else T3 has type equate T2, T3. And the idea was that basically equate gives you nothing. It's undefined if T2 and T3 are different. Otherwise, you get T2, which is T3. That make sense? Oh, do you have a question? Sorry? No, that's a meta-language function. This is, oh, sorry, yeah, that's a good question. This is in the meta-language. It's not in the language. This is going to be a type. Oh, right, I might have written it this way last time, which might make it a little clearer. But I said, like, on the side, T equals equate T2, T3. And then just wrote T over here, or T4. Let's be consistent and number things. Okay? So this is just a restructuring of the static typing rule for if. Kind of make sense? Okay. So let me push this up a bit and say, often when you're designing a type system, in many cases, I talk about this idea of proving semantic type safety, or semantic type soundness, and in a lot of type systems, you can prove it as a corollary of syntactic type safety. Like for your intrinsic type system, the definedness of your language, the thing that you did progress and preservation, can be the tools that you use to prove that the semantic judgment holds. So in a certain sense, what that's saying is there's something about the structure of the safety proof that is helping you realize why the semantic thing holds, right? I mean, in the end, the soundness proof is saying if the syntactic safety proof holds, then the semantic safety one holds. But in any case, there's something about being able to say, oh, if I've typed something and I prove progress and preservation, and I use that to prove semantic soundness, then hidden somewhere in your safety proof is the kind of key to understanding why your language is sound. So it's like our syntactic definedness property induces a meaningful property. So that ends up being kind of the key to the magic trick that I'm going to play, where what I'm technically going to do is I'm going to pull GBA, which is the type-based version, out of a hat by simply adding, mixing in imprecision. We good? Okay, so need a few pieces. I said last time that we introduce a new, thanks to Jeremy Seek, we introduce a new operation called consistency. And this is kind of its definition. It lifts equality across imprecision and says that two gradual types are consistent if there's at least one static type that could justify it. Okay? So let me give you a few examples of consistency just to get you rolling. It turns out that if you follow this, and that's the definition of precision, you can write it out like however you like. Int is consistent with bool, right? Because the rationale here is int and bool up here were already fully precise, and when you what am I saying? I meant to say int is consistent with int. Woo! This is what happens when you get here and discover the coffee shop is closed because it's Saturday. So int kind of represents itself, and it turns out when you pull it down, they're precise to themselves by reflexivity, and they're equal. So, boom. Okay, now let me tell a different truth, which is that int is not consistent with bool. And it's the same argument. It's fully precise, and they weren't equal, so they're not. There is nothing there's nothing that's more precise than both int and bool that makes them both equal. That's kind of the way you want to think of it. Think of gradual types as like bubbles, and what you're trying to do is, as far as equality goes, you're trying to kind of see if there's an overlap. specifically for equality. Make sense? Okay, so the way I think about this in the case of particularly what I sometimes call consistent equality, but it's typically called consistency in the literature unless there's like Garcia is an author on the paper. I shouldn't say that because I'm going to get like pegged in reviews on double-blind stuff. Anyway, what ends up happening is you're basically thinking like, oh, I've now kind of turned each of my points into bubbles and I'm going to take an intersection. But what I'm going to do is instead of literally taking a set theoretic intersection, I'm going to use, so you can think of the precision as looking kind of like a containment, except that somebody chopped off its nose and it's like boxy. So if you think of precision this way, it's kind of like that, right? And then usually intersection is like that. So we're going to use this symbol, which is the nose chopped off version, to describe what it is to take two gradual types and take their intersection. And in lattice theory, this is called the meet. The way to remember that this is called the meet is that if the middle drips a bit and kind of then you've got an M, and it's a meet. Literally, this is the only way I can ever remember this. Oh, and the opposite is called a join, because if you get lazy or you trip, then yeah, it's a J. So, okay, so this is basically taking the gradual type intersection of two types, and it ends up being defined. We can do it kind of intuitively, but you can also do it mathematically. I'm going to do it intuitively right now, and I'll say that if you have int and int, that's going to be int, right? Because the overlap of the two kind of sets totally overlaps, and that's all you get. Similarly for bool, but if you do int and bool, I already said that they're not equal. They're already fully precise. It's like you have singleton sets, so their intersection is going to be nothing. So int intersect bool is not defined. Right? Make sense? Okay. Oh, yeah. Why isn't it question mark?
Why is it undefined and not question mark?
Oh, why is it undefined and not question mark? So,
oh, the mean, yes, of course, it's below.
Yeah. Oh, right. So what I should say is, usually when you think about these operations, you're thinking in terms of a lower bound or an upper bound. Well, if you're thinking order-wise, if you take set containment as being an ordering on things, then you know that if I take two sets and I take their intersection, it's going to be smaller than both of them, so it's a lower bound. And I sort of think of this thing as it's the pile driver shooting up from below, uppercut, fatality, Raiden wins. You look at which way the pile driver is going. That's how I remember which one's the lower bound or the upper bound. And then the other one is from above, sweet, ninja move. Okay. So that's why this one's not defined. There is no lower bound on this in this picture. However, if I take question mark and nat, or nat and question mark, it doesn't really matter, it's symmetric. Nat is below both of them, right? So if I have, I've been saying int all this time. Okay, int is the new nat. So if I have nat and question mark, and I want all my writing on the board to be inconsistent, so when people look at pictures later, they're like, what the heck? So then this is nat. Make sense? So you can use the picture here to guide your intuition about what happens when you bang things together. Cool? Okay, so when I was a kid, there was this old Folgers Crystals commercial, and Folgers Crystals is bad coffee from before good coffee existed in the US. And there'd be this commercial where they're oh, we're on secret hidden camera, and we've secretly replaced your coffee with Folgers Crystals. Let's see what you think. You're the Folgers Crystals is delicious. It's tasty, right? And then so people go out and buy it, and it's horrible, and they throw it away. Ideally, that doesn't happen in this case, But what I wanted to say is like, what we're basically going to do is do like the Folgers Crystals commercial and secretly replace equate with meet. And if you sort of think about it, what equate was doing is basically taking the intersection of just stuff down here, these singleton set kind of things, because this didn't exist yet, right? You're like, oh, do these overlap? And if they do, then produce the result of the overlap. Take the intersection. Whereas now we've got like a real like super duper intersection that does interesting things. So simply just pop that into the typing judgment. Make sense so far? Okay. Similarly, what we're going to do is replace equality with consistency. So now I've talked a lot about the idea that typing is about compositional modular reasoning. And in our case, it's sort of syntax directed. We have a syntax directed type system. And now literally at every level of my program, I've added the opportunity to sneak in a question mark. So here's where a subtle key comes in, that I need to add a feature to TBA that I did add to MBA in order to make this all work out, which is TBA had this nice feature that you just write down the program and all the types magically appear. And it's always the best types that you could get, because there's only one. Suddenly, we now have a language where you could have sort of imprecise types, but you don't want your type system deciding to throw garbage at you whenever it feels like it. However, as the programmer, you may want to say, type system, like, go to sleep. And then it's like, I do not know the directions to go to sleep. No, not Siri, type system, go to sleep. So we add a feature which is usually boring and has no life to it to our language called ascription. And that allows the programmer, by being able to say something like this, it allows the programmer to make a claim about a type. And once you add this thing here, you want to be able to sometimes say, I'm going to say at this border in my program, I'm going to disavow any knowledge that I have of what the type is of the thing inside. That's kind of a lot like, oh, is he going to do it in the right direction this time? Yes, lifting static language. Yeah, so it's kind of like that. You're saying like it's now like static is the new dynamic. I've lifted it up, but it's at the type level. I could say instead, some term has type question mark. So I've made a local decision to lose precision on my types as the programmer. It's my choice. And you can use this feature added to this language to lift all the way back up to here, which gets translated to here. You could translate either of these languages to there, since you can do that one, because it's sort of like the two mashed together. Right? So it's kind of the foundation for your multi-language world, your multi-precision world.
You said it was called ascription?
Ascription, yeah. I always use the Haskell notation because I think the two colons look really cute. I don't like the single colon, but that's just me. No offense to anybody else, so I apparently don't actually program. So we can play this game with each of the rules in the language. So what I'll do is I'm going to write down the rule for pred. Which is T has, the usual TBA rule for pred is T has type net, then pred of T has type net. And what I want you to do is see if you can gradualize that rule, kind of using the formula that I said. So do it in two steps. First, like side conditionify it, and then gradualize it. Okay, like talk to your neighbor, give you maybe 3 minutes, go for it. And you can be loud. It's Saturday. Saturday school. So throw a lecture or a bone here. What are some ideas you had about how you might gradualize this one? Or take the first step and side conditionify it. Replace this one with T1 and T2? Sounds good. Generalize. T1 and T2. Now I've broken my type system. Yeah. So T1 is consistent with nat. So you jump the gun, which is OK. So you start with like T1 equals nat, and T1 is consistent with nat. But that's cool. Yeah?
And then T2 is consistent with 3.
Ah, interesting. OK. So T1 is consistent with T2. Interesting. Oh, yeah. You want to say that T2 is consistent with T1 meet nat. Interesting. Okay. Oh, let me keep these up. T2 is consistent with T1 meet nat. Okay. So first, can you remind me your name? Yeah. Oh, did you have an? Sorry. Before I go in, did you have another?
I have another idea.
Oh, okay. Ah, T2 is equal to nat. Okay. So we've got some options here. Okay, so I'm going to start with Luke. Tell me about your thinking process. I just want to know how you thought through this.
I mean, probably just by analogy with the first one, but then but it should be we're using it as a nat. So in the same way we're using T1 as a bool, so it has to be consistent with the bool. We want this to be consistent with the
Right. So you're like, hey, we want to, by analogy with the first rule, we want to make sure that things are consistent. Okay. So let's keep that in mind. And then JM, right? You said. Predecessor, please be nat. Okay. Ah, okay. It's like you believe that the predecessor should be nat. But you're wary of making it that specific. Okay, so we have we want to reason consistently, and we want T1 to be nat. And then I'm sorry, I keep forgetting your name. Marcus. What was your reasoning about T1 equals nat?
Because from the idea of semantic typing, the predecessor will always be a natural or it will be an error.
Right. So Marcus's reasoning is going from the semantics of what should the semantics of applying pred to something be, and it's like the result of calling pred should be a number or error, so I'm going to expect it to actually be nat. Did somebody raise a hand while I was? Yeah.
Yeah, so using a single big T for T1 and T2 is probably not gradualizing enough. Is that the case?
Ah, so your suggestion was let's just put a T on top and then a T on the bottom.
And then just have one side condition, T is consistent with that.
Oh, and then say whatever it is, T is consistent with nat.
Yeah.
Okay, interesting. Let me write that down. So it's make it all T, and then such that T is consistent with nat. Okay, these are all great thoughts thinking through this process. This is not a trivial thinking process, and it's interesting because you're each using different kinds of tools to think through it. Consistency, thoughts about how precise things ought to be, semantic typing, And like you try to end up bringing all these tools to bear to think about what's going on. So this is great. We've got this nice laundry list. So let me kind of bring those together in a bit. So if I said that if T had some type here, then whatever type that had, it's down here as long as it's consistent with nat. We can think about that by, another way to think about that hacker style is by inlining, right? Because there's only two things that are consistent with nat in our system. This is the nice thing about working in a language with two types, or three types. It'd be like, okay, so I could say, if T is nat, then pred is nat, or if T is question mark, then pred is question mark. That would be those typing rules. So it's interesting because if you write that system, what you're sort of doing is saying local loss of precision eats the world. It'll work its way outwards in my program. And it's unstoppable. It's like, it's Kimmy Smith. Like, so for the purpose of our sort of low-level foundational language, that might be too much imprecision in that system. You might design a language at a higher level that has that feature, and then you might want to allow someone to build a language which has more staticness in it, more precision in it at this low level. Cool? So then Marcus and JM were talking about I really sort of feel like the result of pred should be nat, semantically and like intuitively, but warily. So it turned like if you go back kind of to the MMBA system that we had and sort of think through what's going on there, if you apply pred to something that's dynamic, you do end up, since pred is always blue in that world, you're going to get a static result at the bottom. So this is where that sort of collapsing of as much of your language as possible into the world of blue while allowing the programmer to fit in red where likely helps you lead your intuitions for what happens in this rule. So what ends up happening is, indeed, this is nat. It's just straight up nat. It's like pred always produces nat. We don't have to worry about that one. And it's basically because pred is blue, even though it's black. I'll underline it. Luckily, we're writing a theoretical language that we're designing up front. We don't have to worry about the possibility that we don't know how to reason about this. So we get to make it blue. And that forces that one to be nat. Then up here, well, this kind of goes, since T2 is now nat, you could write T1 is now nat, which is the same thing as this one, which is sort of the same thing as that one. So, well, this one collapses into a pit of doom. So really, it ends up being T1 is consistent with nat. And so you could have written the original static rule as part of what guides is if you'd written it without doing consistency, you might do T1, T2, T1 equals nat, T2 equals nat. But a key for understanding the bottom here is sort of like, yeah, this is kind of a function of the stuff in your premise. But in this case, it's a zero-ary function of the things in your premise. It's like always going to be nat in the static world. It never varied depending on what was going on in the body of the thing that you got. Does that kind of intuition make sense? Yeah, Luke.
Can you systematic about it and saying, after all that, T1 means nat is nat, and then T1 is consistent with nat?
Oh, so okay. So what you were saying was you're trying to throw meat in there. JM, sorry. Oh, sure. Go ahead. If it's not consistent with nat, then we can get away with it being undefined. Okay. Okay, yeah. So it is going to be the case that if T1 meet nat is defined, then T1 is consistent with nat. That's going to always be true because of the nature of meet and its relationship with consistency. So what I'm going to say is the thing that makes my argument for not using meet is because in the original version of this, where I just put equalities on the side, I never wrote down equate. I never felt that I needed to equate the premise with the conclusion in order to capture the notion of my type system. So the meat appeared because equate was there, because like equate becomes meat. Does that make sense? Yeah, so I mean, I'm showing you all these new pieces. It's not obvious how they all fit together. And what I wanted to say is you sort of systematically lift it after you've transformed your typing judgment into like, what is the relationships between the types? Treating all of these as kind of outputs from calling type check on that, and then like connecting them together and then saying, this is a function of stuff after you've connected stuff. Good? Can I repeat all what I just said? Okay, so what you do is first you kind of generalize the type here because it's now you don't know exactly what it's going to be, because now there's like multiple types that could come from things. And then you put side conditions that are often like maybe subtyping or equality or things like that that relate your static content, but make them explicit as side conditions. One of the nice things about doing it this way is it makes writing a type checker a lot easier because you just sort of follow your nose. You're like call type check if they're equal, if they don't fail. The way we write it using pattern matching makes that kind of computational process less obvious. But where it helps here is that we make explicit the conditions among our premises, and we make explicit that the type here is likely a function of the types of the premises or things like that. Then we lift each of those to account for the possibility of gradual imprecision. Good? Yeah? Sorry? That's right. In this language, that's the only place where it happens. Maybe.
So if you have the P1 consistent with that, so after that you have an act consistent with the next rule that you apply.
Oh, like if you keep going, working your way down. Yeah, each one would likely have like consistencies. And if you look at all the other rules, if you remove if from the language, the rest of the rules are going to have like kind of a form that's more similar to this. In many ways, if is the most complicated rule.
But transitive closure is not a generic property in a complicated language, right? For your consistency.
Say that again really loud.
Consistency, transitive closure for consistency is not a generic property for more complicated languages, right? So there are one or two.
Okay, I'm gonna double down on that. Consistency is not transitive, full stop. This is really important. This is one of the major ideas in what happens here. What I mean by that is, when you start playing with the definition of consistency and precision, you suddenly notice, hey, wait a second. Int is consistent with question mark, and question mark is consistent with bool. But int is definitely not consistent with bool. Not transitive, right? You're like, okay, blah, 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 lattice theory, math, blah, blah, blah. Now, the reason this ends up being really important is because when we go to start thinking about how syntactic type safety works, we will find that our reasoning, and it becomes more explicit when you add all these side conditions on the side and are explicit about it, the reasoning in the type safety proof often involves reasoning about transitivity of equality on types. Or if you have a language with subtyping, you're reasoning about transitivity of subtyping. And you make these sort of implicit steps in your proof that you sort of don't notice, especially if you're doing it in pattern matching style. Kind of make sense? Okay, so let's kind of, I don't have a lot of time to give you the full spiel, but let me give you a little piece of it. The idea is, let's suppose there's a couple of bits here that are useful. Especially with an intrinsically typed language, you know, you've got your typing judgment. well, I shouldn't write it up there. You've got your typing judgment, right? What we often think is like, I've got a program, like, I was going to say Joe programmer, but it's Ron programmer, writes a program, and then is like, oh, okay, so I want to run it on TBA, so what do? I type check it. And then the way I think about this is, is my program well typed? And you're like, yes, proceed to run, right? Or, no, get out of here. Like, bad error message that won't help you solve your problems. Like, go home. So, if you think back to last week, there were some points where Bob was talking about this concept he calls Boolean blindness, where he's like, yeah, we think a lot about Booleans. And I was like, I heard him say that, and I was like, yeah, that's a thing. We kind of think about, especially if you're used to the intrinsic mindset, or the extrinsic mindset, you think of a type checker as a filter that lets some programs through and then kicks some out the door. And that's the end of the story. Let me tell you a different story about type checking, which removes the window and says, it's like, pulls you out of the matrix and says, like, what if I told you that typing judgments had content? So you take the red pill, bad things happen, you're not a great actor, but you can program. Although every once in a while you do a good movie about being a hitman that's great on an airplane. And then what you discover is typing judgments have content behind them. And the content is our typing derivation tree. So, and since the language is intrinsic, it's sort of what we're saying is like, this is part of the description of what counts as a program altogether. All this content, all this juice up here. And we're just throwing it away and turning it into yes or no. Why do we do that? Well, because we want our programs to run reasonably fast, and we don't like programming derivation trees. Unless you're Neil, who is really good at this. It's kind of terrifying. It's like, I'm going to have to rethink my whole programming metaphor. So unless you've got the Emacs foo, you usually think here, even though there's a whole new world above you with derivation trees and stuff. So I've often really liked to replace the term type checking with type reconstruction. We often kind of use words like type checking, type inference, and then we're a little loosey-goosey about what's going on there. What I like to say is in reality, when we write this down, it's just because we're too lazy to write this, or we're just not as good in Emacs. And this is really the thing we're writing, and we just want the computer to do program synthesis for us. So we're really reconstructing the real program. So type reconstruction is how I think about it. And that includes, that includes plain old type checking for TBA, because what pops out of your type reconstructor is a typing derivation, evidence that your program is well typed, not just the fact that it's well typed. And that doesn't matter if you left out typing annotations. The type reconstructor will fit them in for you. Or even if you don't have any and you never needed them, it still fits them in for you. This is the program. Not that I actually want you to program with these things. Well, now I kind of want to, but I'm going to need some practice. So then part of building a language that's static is we prove the coherence property that progress and preservation hold, right? So we say if T has a type, T, and it takes a step, well, not everyone does, but we often do, and it goes step to some T prime, then that has the same type. We'll combine progress and preservation together for a moment. Part of the reason is if you were to look at the BA language, right, which has font statics with the check mark, and I wrote down progress and preservation statements for that language, which has a very uninteresting semantics or static type system. And I think if I remember right, let me go back in time. Yeah, so when I wrote down preservation, I was like, it's kind of vacuous, because you're sort of like, if a program steps to a program, then it's a program, right? So you're like, oh, this preservation thing is kind of vacuous because the program is the derivation tree, basically. You can make an isomorphism between the, you can show that your representation, if you wrote a data type to represent your typing derivation for the dynamic language, it will be exactly the same thing as the program that you started with. There's one rule for each term, and it just kind of unfolds. And so you can just say, I'm just going to make believe that my original program was exactly the typing derivation. Or maybe I change if and replace it with like capital D if, because it's like a derivation of if, which has 3 things that says they're okay. Does that make sense? Okay, I'll keep going because it's Saturday. But more the idea is that when you have a richer type structure in your language, this thing doesn't necessarily look exactly like the program that you wrote down. And in the case of, even in the case of the TBA language, it doesn't, because you have all this extra information, all this rich information that's buried in your side conditions. But let's take a moment and kind of imagine that you had wicked like Unicode fingers, and you could program in this, and you were comfortable writing your operational semantics in terms of like evaluation contexts over derivation trees. Where you're like, oh, a derivation tree steps to another derivation tree. And then I'm going to have written that as my operational semantics. Right, so this will be D1, and this will be D2. Kind of make sense? Well, except for the fact that you're programming with derivation trees and then writing evaluation contexts over derivation trees. But you could always write a data structure that represents a derivation tree. Redx does that. If you write like, you know, show derivation, it will give you like a list of stuff, which is just a data representation of a tree that's flat because it's a list. So the representation doesn't matter, but the idea matters, that we have a D1 and we have a D2. And if I wrote my operational semantics directly in terms of moving one derivation tree to another derivation tree, then once again, preservation becomes vacuous because I defined it in terms of one typing derivation tree goes to another typing derivation tree. Then my only concern becomes progress, right? Is this all too high level? Any questions? Yeah.
At the end of the phases, are you just going to let any program run because you can't use derivation?
That's great. So you're like, are you just going to let any program run because consistency is not transitive? Definitely not. That's kind of that's really ends up being the special sauce. So is your name Just? Just. Okay. Yeah. So what Just is getting at is that when you write, when I try to prove progress, and I'm proving progress on these derivation trees, let me give you a concrete example, if I may. And I'm going to do it in SOS style because it'll match up a little better to the thinking that's going on. Let's say I have the rule that says if T1 steps to T1 prime, then if T1, then T2, else T3 steps to if T1 prime, then T2 else T3, right? So this would be the SOS rule for stepping an if. Now, if we sort of blow this up into a typing derivation, what ends up happening is proving progress is proving both preservation and progress at the same time, which is to say, suppose I have a typing derivation of this form. And we know that T1 is actually a derivation tree for T1 is bool. So we're really like, T1 bool steps to T1 prime bool. And right now I'm just in the static world. I'm just talking about the TBA language. Then what I want to show is that I'm going to have like the two pieces. I'm not going to write it out because this is what happens when you hit the third dimension basically because of extra arguments. But you're like, yeah, so I already know that T2 and T3 have types. Those types are the same. And then I know that T1 bool, I have a computational method of turning that derivation tree into this derivation tree and plugging it back into this bigger derivation tree, right? So there's this sort of question like, what kind of rewrites are happening up in this thing to build this derivation tree? And more importantly, if I go to the gradual world, I don't know that T1 has type bool. What I know is that T1 has type T1, and I want to preserve exactly my types for various technical reasons I can't get in. That mostly like I have to be careful about messing up my system, so I always want to say that because my language is intrinsically typed and it intrinsically has a type, I want my program to always intrinsically have the same type at every point in computation. I don't want to mess with my properties. So I've got this, but then somewhere off on the side, I have to have some information about why do I believe that T1 is consistent to bool. And then it's sort of like, well, what counts as information that, like, why would I believe at this point in time in my program that the static type at the beginning of time actually is consistent to bool? Because things migrate over time, right? Dynamic things pass into the static world. So roughly, here's what roughly happens to explain this. Let's say in my static program, I have a point where I have I end up judging that question mark is consistent with bool, right? So you're like, oh, okay, so what this tells me is that the question mark sort of represents possibly int or bool. And I'll write an I and a B. And then this is really just B. And then somehow I have to find at least one thing in this set that is equal to that, to something in that set, right? Similarly, if I end up in a situation where I need to show that question mark is consistent with question mark, maybe because of ascription, then I now need to find at least one thing in here that's consistent with another thing there. And we're talking about our source program. Now, the interesting thing is there's more than one answer in this case, right? So it's actually two possible answers. At the beginning of time, I'm like, all I know is that either int is equal to int or bool is equal to bool, and that's the support that I have for the possibility that this static type is equal to that static type. So now I have kind of computational content backing up this judgment. Does that kind of make sense? So now all of my side conditions are carrying around what I've in the past at least called evidence for the possibility that question mark is consistent with question mark. So now, as you're running your program and you're doing your progress proof, and your progress proof is your preservation proof because you're building a derivation tree, you will come to points where you say like, yeah, at some point in time, I knew that int was consistent to question mark, and then I may end up trying to prove that transitivity holds with, say, question mark consistent to bool. Make sense? So in here, what I end up with is like, I've got a bubble, I've got int over here, I had question mark over here, which had int and bool, but then only this is the only one that works, right? So you just collect the ones that work, and you say like, goodbye. So what I've got is like, over here I've got, yeah, it could be int, and over there I say, yeah, it could be int. And these are sort of like evidence. They're sort of like they inhabit the judgment that int is consistent with question mark. So now when I do composition with, and question mark with bool ends up having the same thing where I say like I started with possibly int and bool. Over here all I've got is bool. So that goes away. So I have an inhabitant of this possibility and an inhabitant of this possibility. And what I need to do is try and prove transitivity, which is I'm going to try and prove that int is consistent to bool. And basically the way I do that is try and find a couple things in the middle and then build a continuous path all the way from this side over to there and then mash it together into two things again. Like collect all the paths that I could have. How many paths do I have in this case? 0. Yeah. So there's like, no, we're hosed here. OK, we're done. So the program dies. So now let me instead try an example that will work. And what we'll do is we'll start with question mark. And we'll go to question mark. And then we'll go to question mark and we'll go to bool. So we start with IB, 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 and B, right? Now, at this point, as I was building this thing and giving it evidence, I can already count out there's no way this program's going to work if I assume int at this point. Over here, I'm like, oh, there's awesome. There's like, int is to int and bool is to bool. So we're good. So now the problem is, can I connect the dots and build a new path and squish things together to get a result? And this is kind of reasoning about the possibility of transitivity in the face of imprecision, which is Just's concern before. So in this case, I'm trying to show that question mark is consistent with bool. So what I do is I see that I can make a path from here to here, to here, to here, and then compress, and then I end up with bool to bool. Kind of roughly make sense what's going on? Now, what ends up looking sort of uninteresting about this particular case is that I have two types in my language, so everything collapses. Things get much more interesting when you add functions. Whoa, like. So if I have types like question mark, arrow, question mark, right? What I'm really going to end up with is, it's not just like, now that I've added question mark, now that I've added arrows, and we're assuming that I have recursive functions, it's not that I only have like one level of functions, right? Like in a functional language, you'd have many. So adding the idea of question mark, arrow, question mark gets particularly rich. And in this case, it's any function from any type to any type, right? Now, how many types do I have when I add functions to TBA? I have an infinite number. So you basically take an infinite number of types, take an infinite number of types, take the cross product, apply pointwise to everything. That's what that represents at that point. So then what happens is when you play this game with like question mark, arrow, may be consistent to question mark, arrow, int, might be consistent to bool, arrow, question mark, might be consistent to question mark, arrow, question mark. You kind of play this out on paper and you start to see like, oh, like interesting things happen. Like at some point I could basically boil down to the idea that if I went from question mark, arrow, question mark, and then am consistent with question mark, arrow, int is consistent with bool, arrow, question mark is consistent with question mark, arrow, question mark, then the question I have is, at the end of the day, can I justify that question mark, arrow, question mark is consistent with question mark, arrow, question mark after all of these steps of reasoning? Yeah? Yeah, you're still commutative if you add functions. If you add subtyping to your language, that goes away. So the way I think about equality is an astonishingly boring instance of subtyping. And that kind of makes it useful. That's a useful metaphor in this context. That's why I actually write T1 is equal to bool, not bool equal to T1, because it's sort of like you're doing subtyping. You're going that way. Like I need to be able to substitute this into a context that wants a bool. Okay, so my question is, if I've done all of this, what's the evidence that I'm going to have here that question mark is consistent with question mark? What's left? Okay, I'll give you a hint. Over here is basically type cross bool, or type cross int. And this is bool cross type. And then you kind of take all of the, then you take all, well, singleton and singleton. And then you try to take all the paths that will go through both of these on your way out. Yeah, so I heard someone say it. All you end up with over here is bool, arrow, int on this side, and bool, arrow, int on this side. So even though your static types have, statically you have no information, you've collected and reduced all the way down to an exactly precise type. So if you try and use this code at anything that's not exactly that, you get an error. Yeah? Ah. Good call. So the worry here is like, dude, we've got like, you're playing with infinite sets as if you could do this in a computer. Like, are you insane? We'll set aside the last question, but more the point is that you don't actually carry around infinite sets of types. You use a technique called abstract interpretation to develop a tractable over-approximation of those possible sets and then compute with those decidably. It's like you're basically doing, it's really weird, you're doing static analysis at runtime on types. And that kind of makes the runtime with all of the derivation trees going. Is it here? Yeah. That's what's happening at runtime here, is you're kind of doing you're basically running type safety at runtime because you can't resolve it completely via type safety proof at the beginning of time. So you can kind of think of it, oh yeah, it's literally dynamic enforcement of types. Yeah? Oh, so they both represent all possible types. It's like you're all kinds of imprecise here. So question mark, arrow, question mark is basically a way of saying, I know I have a function. I have absolutely no idea which one. So it's like the set of all function types is kind of how you want to think about it. We're doing kind of like, imagine having like, taking all of your constructors and then mapping them. And now but over sets. So it's like set map on constructors and then question mark is everything. No, we don't, there's no equations between them. You're just sort of like, I've got independent bubbles and what's in them. Cool? Though an interesting idea, and I think people have worked on that. Or thought about it at least. So the basic point here is that if you play this game and run it all the way through, then what you find is that out pops this thing, which is basically that thing, which is that thing, which contains those things. And really the main point is we really followed our nose very systematically and kind of magically popped out a gradual language which lets us combine the static and dynamic languages just by starting from the static type principles that a type safety proof gives you. So I wrote a paper about this. I hear it's like half readable. But ideally, you get some high-level intuition of what's going on here. And it might be worth, the nice thing about playing with this in the context of the BA language is you don't have to worry about the infinite type problem. So you can just say, I'm just going to carry around sets of types since there's only at most 2 of them. And then just like write yourself a regex model that plays that game where type type checking builds you a derivation tree, but then you always carry around the set of what types could possibly be equal at every point, and then whack them together, and you could just make that run. Okay, so I've gone over a lot, and so I will stop there. And first, let me take some questions, if there are any. Yeah. Oh, how does precision work on question mark? Right.
Like for consistency, but you always you want consistency U2 because T1 is that step less than the U1 and T2. Or so there's this T1 and T2 such that they're equal and they're both less than U1 and U2. But like if for the question mark in the argument position, is there like a constant variance sense in the sense that if for something to be consistent, it might be not less than but greater than?
Are you asking a question about how to define consistency?
Consistency, yeah, I guess consistency for the function type.
Ah, okay. So I'll give you a brief answer to give you a sense, and then the main answer is try and read the first half of the paper. I think it does a pretty reasonable job of explaining how to define precision. I didn't want to get into the technical machinery of how to define consistency, but the rough intuition is that like question mark, arrow, question mark is, the only things that are less precise than it have to be functions. And I've like, this is totally unchained, so it could be anything, including like question mark, arrow, question mark. This one could be unchained, question mark, arrow, question mark, and you kind of keep working your way down. So you keep, like almost think of, you can think of question mark almost like you're in Agda, and you keep like popping in like new like partial types with more question marks until you hit like first order type. So the lattice works its way downward that way. So given that, and given my general definition of consistency as like down precision, across equality, up precision, that's the four-way diagram, then you can figure out everything else. But there are, and the first paper on gradual typing has an inductive definition of it, because we didn't think of it that way at the time. It's been a journey of understanding. Other questions? Oh, sorry. This paper is called Abstracting Gradual Typing, and it appeared in POPL 2016. Okay, I'll leave it there with like research highlights. So go forth and like gradualize things, or think about, choose, which camp are you in? Are you in intrinsic? Are you in extrinsic? Are you in forward? Are you in backwards? Can you not choose, so you choose them all? I hope that you've found some of this kind of at least mind-bending, if not compelling. And thank you for your time. It's been an honor and a privilege to teach you all here. I've had an absolute blast. It's been amazing. Come say hi, keep in touch, and thanks.